Hello, I'm Breno Avancini from the University of São Paulo, and today I'll present the numerical modeling of fluids mixture flow in high velocities with phase change. Oil wells and biogas production centers have important energetic potential, mainly for the production of methane, but the gases from those sources have high concentrations of carbon dioxide. And we showed here in the left table the typical composition of the gas streams coming from biogas centers and from the pre-salt natural gas. And as you can see, the concentration of carbon dioxide is high. And in order to meet the gas composition requirements from A and P, which are shown here in the right table, an upgrade process can be used. And the method for capture the carbon dioxide, we have 4 of them listed here. The first one is the adsorption process, which utilizes material with a specific porosity that has affinity with the adsorbed gas. Amine towers, which uses the special solutions that absorb the carbon dioxide molecules from the gas stream. We have also semi-permeable membranes unities, which uses membranes that have selective diffusion capacity, and cryogenic process, in which the temperature reduction of the mixture gets one of the gas species to the saturation state. Here we highlight the supersonic gas separator, which are the object of study of this research, in which it uses the cooling by expansion of the gases to reach the saturation point of one of the species of the mixture. And during the condensation process, liquid droplets are formed in the stream. And in order to collect these droplets, an introduction of a secondary rotational flow to centrifuge the droplets formed during the condensation process. And eventually the liquid droplets will form a film in the wall region of the device and will be collected and extracted from the mainstream. So the objectives and contributions of our research: first, the objectives are to make a one-dimensional flow numerical model for condensating compressible flow, make the numerical model validation with experimental data available in the literature, and carry out numerical simulations and analysis and sensitivity analysis of the flow of methane and carbon dioxide mixture. And our main contribution is the development of a one-dimensional numerical model, which is transitory, model the condensation process of the flow, and also consider the mixture as a real gas. And for that, we apply some equations. First, we apply the continuity, the momentum conservation, and the first law of thermodynamics, which are the first, second, and third rows here of the system of partial differential equations. And we also applied the equations of the method of momenta for condensate transport equations, which are presented also here in the system. And after that, to close our equations, we applied the real gas equation of state in our model. And in order to solve the system of partial differential equations, we applied a numerical scheme AUSM dV, which calculates the interface flux term of the solution. And this term is calculated using the equations from 2 to 5. And we also implemented the package cuprop, which solved for us the equation of state 6. For the validation purpose, we used the geometry and experimental data presented by Moses in 1978 and selected the cases 193 and 424 to simulate and compare the results to validate our model. Here I present the results of the case 193. Here we applied 3 different numerical models for the nucleation process. From those 3, we saw that the non-isothermal plastic nucleation theory had better agreement to the experimental measurements, And because of that, we also changed to see the difference between the two models of radius growth, which are the Giarmati and Young models of radius growth. And after carrying out the simulations, we compared the experimental results, which are represented here by the black triangles. And we also make the calculation of the error between the numerical model and the experimental data. And as you can see here in the right graph, the two models, the non-isothermal classic nucleation theory with the Giarmati radius growth model, and the non-isothermal classic nucleation theory with the Young radius growth model, have both good agreement with the experimental data available. And after the analysis, the validation of our model, we carry out some sensitivity analysis. And for that, we used the nozzle geometry presented by Sun in 2017 and used the boundary conditions shown here in the table. And as you can see, we used 3 different total pressure values and also 3 different molar fraction of methane values. And the results of our sensitivity analysis are presented here. And we conclude that the maximum, from this analysis, we conclude that the maximum variation in the methane concentration is determined by the inlet concentration due to the asymptotic behavior of the molar fraction curve during the expansion process. And we also saw that more than one pass might be necessary to upgrade the gas to the desired composition, also due to the asymptotic behavior. So if you want to go to 60 to 80% of methane, you might need one pass, recompression, other pass, recompression, and finally another pass to reach your desired composition, for example. And in the analysis of the variation of pressure, we saw that the increase of pressure also increases the change of molar fraction in a single expansion. So as you can see, with 4 megapascal, we went to something like 75% of methane. And with 6 megapascal, we went to something like 78% of methane. So some conclusions: the one-dimensional model is very efficient to verify the fluid flow behavior. Results of flow with the condensation process were obtained. The model predictions agreed with experimental data, and it's possible to identify the condensation wave location with the model results. This is a very important aspect, because to project the device, you have to know where the condensation will happen, so you can place in a good place your collector. And we can predict also with this model the maximum capacity of a carbon dioxide removal from the stream. Some later results, we also managed to validate our one-dimensional model in multi-component flow. We are working some future works. We are working in a parametric study of the nozzle geometry. We are also working in a 3D flow model based on OpenFlow. We have simulation. We're going to carry out simulations of turbulent compressible with phase change flow, and simulations of the whole device, and the sensitivity analysis will be performed. The development of a control system for the device is also planned. Those are some references used in the presentation. I would like to acknowledge special thanks to Clark Solutions for the financial support for me to be in this research, and also for PPG-EM from NUS for the financial support to be here in this conference. And that's it. I hope you all enjoyed the presentation and have good questions. Thank you all.